thanks for your attending the talk. Let me introduce her briefly. Kelsey is now working at the DeepMind, right?
Yep.
Yeah, and she recently finished her PhD at MIT. And we wanna listen to her talk now. Yeah, please go get started, Kelsey.
All right, just let me see if I can move this Zoom. Can you just see my screen, or do you also see yourself in the side of my screen?
We just see the screen well.
Okay, perfect. Okay. All right, yes, thanks so much for having me. I'm pretty excited to tell you about my work today, studying physical problem solving in both humans and machines. And just so you know, I have a background mostly in computational cognitive science, so this talk is going to be more focused on sort of what we can learn from humans to try to build sort of more safe and predictable kinds of robotic agents. So first, I just wanted to prompt you to think about what it actually means for robots to be safe. So I think many of us understand that many of these methods that are trained with these big model-free deep reinforcement learning techniques like this one often don't feel particularly safe. They do these pretty crazy, unexpected things that seem pretty unrelated to the task they actually need to solve, like pumping their arms into the sky as they navigate terrain. But designing controllers for everything also doesn't necessarily make a robot safe, because if the assumptions that the controller uses are violated, like seems to be often the case in transferring from simulation to the real world, those robots might fail in surprising ways, like in trying to open a door like here. But even human behavior doesn't always feel quote unquote safe. I like this particular example of a child building a block tower, and originally this seems like everything is going quite well. They're making this pretty awesome tower, but they seem a little unstable. And then as they try to do it, they unfortunately fall and just totally wreck the entire tower. So from one angle, this behavior really doesn't seem safe. It's not robust. This child fell over and broke the object they were trying to build. But from another angle, this is still much safer than those robotics examples, because while their behavior isn't perfect, we could still pretty easily predict what kinds of things this kid would actually do. We can guess at what their goals are, how they're trying to achieve them, and even have a sense that their footing might be a bit unstable so that we could try to intervene and help. And so safe behaviors might not necessarily be perfect behaviors, but rather predictable behaviors for humans. And making behavior predictable, especially in the real world, might require both learning and more classic control. So my research studies humans and machines to better understand how to make machines that are more human-like, with an eye to making them safer to interact with. And I work in the space mostly of physical problem solving, where machines need to manipulate objects to solve complex tasks like tool use and construction. And as you can probably guess, I think that performing these things at a human-like level for these kinds of tasks is likely going to require a mixture of learning and structured knowledge, which is really the theme of this workshop. And I think as a computational cognitive scientist, this structured knowledge is going to come from our studies of humans, as well as all of the study that we do on robotic systems. So for example, based on our studies of infants, we really believe that even at the youngest ages, humans represent the world according to objects. And by childhood and certainly adulthood, people understand that those objects obey the laws of physics, which governs how they move through space and time. And we know that animals across the intelligence spectrum, really, all the way from mice up to humans, don't seem to represent actions or time as this continuous unbroken stream, but rather as a sequence of discrete events or modes. So I'm going to propose that these three ingredients plus learning form the basis for physical problem solving in humans, and we should therefore take advantage of them when building machine agents by baking them in, if you will. So first, I'll show you that with a more appropriately structured relational action space in the policy of these deep reinforcement learning agents, we can make those deep reinforcement learning agents as flexible as people for a physical construction task in ways that also allow them to generalize very predictably to new kinds of problems. We can build on both these relational and physical structures by recognizing that they're differentiable, which also lets us take advantage of these powerful solvers to perform much more complex long horizon tasks that safely respect environmental constraints. And with just a little bit of learning, we can relax some of these strict assumptions about the kinds of knowledge that we build into these robotic systems in order to improve their adaptivity and robustness, both relative to machine learning systems, but also relative to classic robotics. So first up, we're going to bake in these relational action spaces. So in the animal kingdom, animals do a really amazing number of different things that are pretty complex. And one of my favorites is something that almost all animals do, which is to construct shelters. And this problem of construction is pretty widespread, from birds building nests to beavers building dams to expert engineers building these skyscrapers in cities. And so in this first project, we were interested in understanding how these deep reinforcement learning systems will be able to handle a slightly simpler task, which involves trying to stabilize a tower by applying glue to joints between blocks. And this is obviously a lot simpler than construction, but it's sort of tractable while still having a very rich action space and complex perceptual input. So great, okay, why is this problem actually hard? Could we just apply these sort of standard deep reinforcement learning techniques here and have it magically work? The answer, of course, the reason I'm telling you this is no. If we were to use these standard deep reinforcement learning agents, we would convert each of these towers to an image or just a giant feature vector of these different block states, pass that to a deep network, and then output a vector that tell us which of these contact points we should glue. But this has perhaps a slightly non-obvious fatal flaw. Because of how this network is set up, and all of these networks are set up, you have to decide all of these gluing points at once. And what this means is that if you add a new action, like perhaps adding a new block to the tower, the agent that you've trained is essentially useless. It's going to have no idea what to do, and you would have to essentially start training again from scratch. The number of actions for most of these systems is fixed, and they don't share representations across actions in any way that will help you with new kinds of problems. And so to remedy this problem, we introduced a relational approach to considering this action space. And here the central idea is to change the representation of the tower from just an image or giant unstructured feature vector to a graph, where each node represents a block and the edges represent their interactions. So now, instead of learning a function that maps an entire tower to an action vector, we'll learn a function that applies locally to an edge in the graph and can be shared across all of the edges. Then for each edge, we can apply the function to determine whether or not we're going to glue it. And because you're sharing the function across edges, any information you learn about one edge can actually be shared immediately with all of the other edges. This allows you to pretty easily now generalize to new sizes of towers, and it's substantially more data efficient because the function is shared in this meaningful way. So we call this idea a relational inductive bias for machine learning, and the type of network we use is called a graph neural network since it operates over graphs. So to confirm our intuition that this relational inductive bias should help with flexibility and better explain human behavior, we compared an unstructured approach, which is more common in deep reinforcement learning, here called just a multi-layer perceptron and labeled as the MLP, with the graph network labeled as GN here, as well as humans. And each of these machine learning methods was trained on 100,000 towers of each size and then tested on 15 held out towers. And we can first look at the total reward achieved by each of these agents, with this dashed line representing the total possible reward across all of the test problems. So humans actually don't do particularly great in this task. They only achieve about half the maximum reward possible, which is not too bad considering that they only had one tower of each size to train on. But what's striking is that these unstructured methods perform really poorly. They perform much worse than humans despite having much more experience. But the graph network models, by comparison, do much better, both better than humans, as well as better than these unstructured methods. But what's cooler is that we can look instead also at the generalization error by looking at how these models perform when they're only trained on a subset of the data. Here, 2 to 6 and 8 to 9 block tower sizes, and look at how the model generalizes to block towers that have either 7 or 10 blocks instead. So when we let the model train on all of the problems, the performance it gets is shown here in blue. And when we train on just the subset that doesn't include these 7 or 10 size block towers, it's remarkably able to do just as well. And this suggests that overall, these relational inductive biases seem to help with both the overall performance, but also the generalization or flexibility of the model. And I also want to mention that I didn't talk about it here, but these same kinds of graph network approaches can be used to predict things like tower stability, which we've shown in other work can lead to much more robust model predictive control. Across a sort of wide variety of different projects, there's been sort of this wave of work on learning these dynamics, models, and policies with graph structure that allow us to do very interesting things. And I want to just quickly highlight some of that. So on the control side, you have papers like this really nice work, NerveNet, which uses a graph neural network to represent the body of an agent to learn locomotive policies, or the one just below it that uses graphs instead to learn a model of a jointed body that can be combined with something like model predictive control. And these can even be applied to learn models from pixels, like Yi et al. Showed in a 2019 Coral paper. And it can be used even for planning problems totally divorced from control to do things like determine which objects are actually going to be relevant for a plan when there are many more objects than you can possibly consider when trying to figure out what to do. So I'm now going to switch gears a little bit to talk more about robotics without learning and how to take even more advantage of physics and structured relational actions to, again, better explain how people actually solve problems. And for this next project, I was really immensely fortunate to work with some amazing robotics colleagues, and much of the credit should go to them. So most systems for planning and control, when a learned world model is involved, at least on the machine learning side, treat that model as essentially a black box. And they assume that the only thing we can do with that model is to pass in a current state in action and get out a state at the next time point. But this is really hugely limiting for long horizon tasks. You're going to quickly experience a ton of model error, and it's only really going to work if we have really strong ideas about which actions to take, or an exceedingly small number of actions that we can even use. So a much better thing that you can do is to actually look inside this box. And if we do that, there's a lot of useful structure in the world dynamics that we can take advantage of to make better model-based plans. So in particular, if we open the box, we can immediately see that much of the world's dynamics can be factored according to these relational modes, which are segments of time for which the relational poses of objects are not changing. So for example, if you pick up an object, really no matter what object it is, assuming you were successful, you're now going to be holding that object and it will move with you wherever you go. Or if one object hits another object, again, at least in broad strokes, no matter which objects they are, this implies an impulse exchange equation between them. And not only is the world relationally factored in this way, but it can also be made to be piecewise differentiable with meaningful gradients, especially when conditioned on these particular relational mode transitions. And this is critical because now we can take advantage of these factorizations and derivatives in both imagining how the world will unfold, but also for making plans. So now the natural question is, if everything is differentiable, are we just done? And we think the answer here is no. Gradients are very powerful when we have them, but there are many problems for which there are zero gradients, like no local improvement that could be made to meaningfully improve your objective. And categorical decisions about what kinds of actions to take, for example, should you push or pull a door open, can lead to a huge number of local optima that are very difficult to deal with. So to make that intuition clear, we can look at the classic way of writing out a planning problem as a nonlinear program, where we try to minimize particular path costs in order to achieve a particular goal from some initial state. And the path you can actually take is going to be constrained. For example, you can't penetrate objects and you can't magically move objects at a distance. But this is a really nice problem formulation. But unfortunately, as written, it's going to suffer from this combinatorial explosion of local minima, like I was just mentioning, because these path constraints H and G are often not smooth and differentiable across the entire configuration space for all of time. So the insight of this paper was that if you condition this optimization problem on high-level modes, S, and mode transitions A, these path constraints of H and G are going to be differentiable and smooth, and in many cases unimodal instead of multimodal. So here, modes are defined simply as relative states of objects that can be achieved. Like if X and Y occupy a stable free mode, this implies there's a stable free joint from X to Y, or the contact mode of applying impulse from X to Y with the resulting differentiable constraints following the impulse exchange equation. And these mode transitions are essentially high-level actions that either the agent can take or that the world can take, which imply particular modes as outcomes plus other kinds of constraints on the path. So an example of this is the transition hit, which applies to two objects and can be accomplished by the world or by an agent, and which implies that the objects X and Y must be touching and end up in the contact mode of exchange impulse, both of which can be written differentiably. And then this logic of mode transitions is going to tell us how modes are connected through actions, which lets us do also this symbolic level planning to get away from this combinatorics of local minima. So with that formulation, planning is now going to become a two-step process where step one is searching through possible high-level actions, and step two is then optimizing a path conditioned on those choices. So to search through these high-level actions, you first need to construct the search tree consisting of all possible sequences. So here's an example incomplete task tree for this problem on the left. In this first step, you could try to grasp the hook or the ball. And given that you grasp the hook, you could try to push the ball with the hook, hit it with the hook, or pass the hook back to your other hand. And this then leads to more options and so forth until you reach the goal, which is to be holding the ball in one of your two hands. Finding a plan that amounts to choosing a branch through this tree and optimizing for a path that satisfies these differentiable constraints implied by the high-level actions along that branch. And if the cost of this resulting path is low, then this set of high-level actions is feasible and can be executed, and otherwise you'll have to try a different sequence of high-level actions. So doing this procedure results in a diverse set of paths that will allow a robot to achieve its goal across a pretty wide range of different scenarios. And this formulation can handle making and breaking contact, both dynamic and kinematic motion, and even complex multi-stage plans, which were all inspired by some experiments that we did on humans that I'm not showing here. It's also trivial for the robot to actually use the environment to its advantage, since the modes and mode transitions apply to arbitrary objects and not just the robot's end effector. But there are limitations, like you probably just saw, such as these very physically unrealistic motions due to essentially hard coding physics as these perfect differentiable constraints. So we never had to really deal with the real world here. So that's pretty cool. We can essentially open this box on world dynamics and use the structure in there to do some really nice planning. But that still isn't the whole story. And because I love videos of humans doing crazy things, let me show you one more. This is an example of a child who clearly doesn't have a perfect understanding of physics and is not using sophisticated knowledge of constraints, but is still able to do this incredible thing of using a locket to escape her own quarantine. To explain this kind of behavior, we'll need to really go beyond this handcrafted knowledge to actually be able to discover modes and constraints, as well as these high-level actions from experience. So I'm going to talk to you about one paper that we've worked on that was presented at ICRA last year. So to do this, we'll start pretty simple to see if we can learn these mode constraints from just a few demonstrations from an expert. And we'll assume that we have a small number of expert demonstrations and that these can be easily segmented by an off-the-shelf segmentation algorithm. And we then want to learn equality constraints, here written as F, parameterized by some set of learnable parameters theta, such that if we use differentiable trajectory optimization with those constraints F of theta, it would be able to reconstruct the expert demonstrations. So the real power of this kind of representation in trying to learn dynamics as constraints is the compositionality of it. And so that's what we focus on in our experiments. So in this first experiment, it's pretty simple. In training, an expert is going to show a reaching trajectory to just a single random point in space. But now in testing, we're going to look at whether the system has learned a constraint that can be reused multiple times, generalized to 2, 4, or even 8 different locations in space. And it can. The model does very well. It can almost perfectly recompose and reuse those constraints that it learned from just a single to about 3 demonstrations for solving a much harder task at test time than it faced at training time. In the second experiment, we looked at whether learned constraints could be composed with other handcrafted constraints. So here we get demos of a gripper picking up a blue object and placing it on a green square. But in testing, it has to avoid this impenetrable pillar that's shown as this white column that lies between the object and the green area, which is now hard-coded in testing rather than learned. But it again is able to handle this almost perfectly because it's just able to learn the constraint, the goal constraint in this case of getting the blue ball into the green area, while also combining that with the impenetrable constraint of moving around the pillar, which is very reassuring and means that we can easily add in our own knowledge about what we want the system to do while also taking advantage of these learnable constraint settings. We can even look at what those constraints look like for the case of, for example, this reach setting and see that they're pretty sensible. So here, each row is showing a constraint with red being a negative weight on that particular feature of either the velocities or the states at time t or time t+1, and blue being a positive weight. And while you can see these are a little bit distributed, with a lot of things not being quite white, which is just not including that at all, the model does essentially learn these spatiotemporal continuity constraints for each of these dimensions. So all that means is that your position at the next time step is equal to your position at the last time step plus your velocity, which is very reassuring to look at. We can also learn and compose multiple constraints, like in this case, where in training, the model sees a hand picking up an object for 4 demonstrations or pushing an object for 4 demonstrations on the top and the bottom respectively. And then in test, we can see whether or not it can learn to combine these things to get the orange block on top of the pink one by first pushing the pink one out from underneath and then picking up the orange one and placing it on top. And it does this essentially perfectly without any issue. Again, just showing the power of using these learned constraint models as opposed to just learning giant black box model dynamics. So we have a little bit more time. So I just want to share one last project with you that attempts to make these more structured planning methods robust to more unexpected aspects of the environment that are very difficult to model. So as many of us here have probably experienced, often our biggest dreams for our robots go unfulfilled. So in simulation, we might have very nicely a robot that does a very nice, straightforward behavior, like use a hook to get an object. But then in the real world or just a new environment, something changes, like perhaps the smoothness of the table, and suddenly everything is bad and the robot no longer does anything correctly. Like in this case where it now has random terrain shown by these little gray blocks that end up causing it to get its hook stuck at various points and not able to achieve its goal of getting the object into the red zone. So how should we actually deal with that kind of situation? Well, it's not really simple to design a new controller for these problems. Some of this variation is very hard to predict or hard to observe, or maybe even both. But learning from scratch is also pretty infeasible. These are very long horizon sparse reward tasks, and deep reinforcement learning is really going to struggle with those. So we proposed a really simple thing you can do, which is surprisingly often super effective, which is just instead of trying to learn the model, just learn a residual policy with deep reinforcement learning to augment the actions proposed by your designed controller. So doing this results in much better behavior, where the robot now successfully handles new kinds of objects and is also very robust to variations in the surface of the table, and strongly outperforms both the initial controller, shown here in blue, as well as a deep RL agent that's shown here in yellow, with our method, this residual policy learning in green, having a much higher test success rate than either of the alternatives. And this can also help you in various other kinds of situations in robotics. So we did a nice test with a setting where a controller was designed for a high friction table surface, and then it was tested when the friction was significantly reduced. And what you can see is that the residual policy learning method is able to do a lot better than the initial controller. It no longer pushes things as hard, and it didn't have to learn actually anything about the model in this case. It's just able to do that learning residual actions. And it can also be used to handle miscalibrated reactive controllers where this initial policy does not have the correct torque to actually grip the object. And RL from scratch just never does anything at all. But then with residual policy learning, it can again very quickly adapt to figure out policies that work very effectively. And the lesson from this is really that we can use controllers from robotics. We don't necessarily have to learn an environment model. We can actually try to augment the policy space directly, and that can be effective in settings where the model is just simply really hard to learn, or you might have partial observability, et cetera, et cetera. And this allows us to preserve a lot of the predictability of our original controllers while also dramatically improving their robustness to new kinds of problems. So thanks very much for baking with me today and listening to what I've told you. I hope you found it interesting. I've shown you a few ingredients that I think are required for making these robotic systems more human-like, and in my opinion, by extension, safer. From these deep relational action spaces accomplished through graph networks, to planning with differentiable dynamic constraints, to learning those constraints from small numbers of demonstrations, and finally to these residual policy learning methods for more robust plan execution. And finally, thanks to my wonderful collaborators, which include a mixture of cognitive scientists, machine learners, and roboticists, as well as my funding sources, and of course, all of you here, especially the workshop organizers, for honoring me by inviting me to come and speak to you today. Happy to take questions if there's time.
Thank you very much, Kelsey, for your very interesting talk. We want to switch to the asking questions. So if someone has questions, please either post in chat or raise hand.
Okay, I have a question. So Kelsey, so you talked about factorized actions. So is there literature in cognitive science that how do humans factorize action or their like environment spaces?
Yeah, definitely. So I didn't talk about this in detail, but there's been decades of work on this topic, actually, all in the space mostly of thinking about it as a hierarchical reinforcement learning problem. And so looking at how people try to learn essentially like options from various kinds of experience. But what's really limiting in a lot of those approaches, and what I think is a very open area actually for cognitive science that will hopefully continue to be informative for robotics, is that much of this has existed in the domain of grid worlds. So just like looking at how people sort of move up, left, right, and that kind of thing, and not really fully engaging with the embodied experience that people have in doing something like tool use. So we looked at this a little bit in collaboration with Marc Toussaint when we wrote that RSS paper, in looking at how people actually solve these tool use problems and sort of segmenting their actions into different types. But I think it's still actually a pretty open area to understand this sort of more interesting, rich space of embodied action and embodied action factorization.
Thank you.
Maybe a follow up on this question. So it seems that being able to do this kind of splitting into modes autonomously is a big question for being able to build more complicated systems. So do you have any additional thoughts on how kind of this logical modes can be inferred especially in an unknown environment? So if we're imagining a robot constructing its understanding of the world in real time, it would be hard to kind of predefine what the modes are. Yeah, I'm curious. I know it's a difficult question.
No, it's a great one. I mean, I think that's one of the most interesting questions right now too. We sort of took some initial steps that I showed in learning these modes, but in settings where the segmentation was easy. And there's a very natural question of what if the segmentation is hard? So I worked on that a little bit in the context of just perception in using techniques from Bayesian non-parametric models, which essentially try to learn how to cluster a space of features while simultaneously figuring out how many clusters there are. And I think clustering might be at least a first step to figuring out something like segmentation, and then transforming transforming that into a constraint-based representation is sort of a second difficult step. And I'm hopeful that maybe some of the more recent techniques in constraint learning could be useful there if we were able to sort of do a first step of segmenting the trajectories. But I do think this is a very interesting open problem, and there's, I think, a lot of ongoing work on this. So it seems very exciting.
Yeah, definitely, I agree.
Any other questions? All right. Yeah. We can move to the next session. Thank you very much, Kelsey.